Good morning to our speaker, Professor Hillebrands, and colleagues from Europe. Good afternoon to friends in Europe, India, and other Asian countries. Or good evening to maybe people in Japan and other places. Thank you so much for joining this lecture. And first of all, on behalf of my team, my co-convener, Dr. Prabhushan Singh, my team member, Puspendra, Shakti, Ajay, and others, I'd like to thank Professor Hillebrands for taking his time to join us for this lecture, which we're very much looking forward from a long time. And I think we will get a very large audience today. I think Professor Hillebrands is very well known in his field, and he doesn't really need any introduction, but just for the benefit of the young students who may not know him. So I know him from my PhD time in Duisburg, and I am very grateful to him because we wrote our review paper in Journal Physics D, and that time I think he was the editor, so he kind of promoted that article. And I'm very happy that that article is now about having 1,000 citations. So let me talk about Professor Hillebrands. He's a full professor working at the University of Kaiserslautern, where he has also served as the Vice President for Research, Technology and Innovation from 2006 to 2014. Besides, between 2016 to 2018, he held the position of Scientific Director and Speaker of the Executive Board at the Leibniz Institute for Solid State Material Research, that is IFW, in Dresden, Germany. His research interests are in the field of spin dynamics, material properties of magnetic thin films, multi-layers, and nanostructures. He particularly focuses on magnonic spintronics or magnonics, the field that treats magnons, the elementary quanta of spin waves, which are the dynamic excitations of a magnetic body. He is also serving as the Vice President of the Academy of Sciences and Literature in Mainz. He is a member of the National Academy of Science and Engineering Germany, that is Academic. He is a fellow of the IEEE Society and the American Physical Society. Regarding his service to the international scientific community, he holds the position of the President of the European Magnetic Association. He is the chair of the C9 Commission on Magnetism of the International Union of Pure and Applied Physics, that is IUPA. He served as the community as a member of many funding boards and scientific advisory boards, including the granting board of collaborative research centers of the Senate of the German Science Foundation, that's Deutsche Forschungsgesellschaft DFG, between 2002 to 2008, and more recently in the position of the chair of the Scientific Advisory Committee of the Helmholtz Center Dresden-Rossendorf in Germany. In 2016, he received the ERC Advanced Grant from the European Commission. Throughout his research path, he has published more than 450 referred articles, 5 patents, and many patent applications, as well as many book contributions and many review articles also, which people like me read and learn a lot. So with this very brief introduction about his academic portfolio, I request him now to give the talk. But before that, I like to mention to the audience that during our lecture, we don't take any questions. So if you have any questions, kindly write in the chat box or raise your hand. And at the end of the lecture, I will take all the questions and we'll discuss. And also at the end of the lecture, I would request all of you to switch on your camera to make a group photo. So with this, thank you so much, Professor Hillebrands, for your time. Now I request you to start your lecture. It's all yours. Thank you.
Yeah, thank you very, very much. So let me get my screen shared. First of all, I would like to say, Sabanka, very much my congratulations to setting up this seminar. We just discussed it a little bit before we started today. I think there are 3 major seminar series now around the world. One is yours, and with a lot of prominence, and this gives especially India the right place where India should stay in the field of science. So today we are discussing magnonics. Advances in coherent magnonics. There are two types of magnonics. One is just diffusive transport and the other is coherent transport. And of course, with such a title, what we have in mind is that we want to use it for something. And essentially what I'm presenting you today is just some considerations, some ideas in the fundamental science domain, but always in view of potential applications. And potential applications, of course, is computers, is information technology. What you see here is an animation which we actually like to show at open days in physics in my university. We put it on a touch screen, so you can touch the screen with your fingers, and each time you touch this array of spins, a spin wave will be created around your finger. We cannot show this here, of course, in this animation, but I think you can very easily see that spin waves are just dynamic excitation of an ordered system of magnetic moments, and they propagate, and if they propagate, they have properties such as amplitudes, just the precession angle here, or the relative phase with respect to some reference phase. And that is, of course, very, very important. So just to put it in the right thing, and why are spin waves so useful? You know very well CMOS technology, but the variable which you can control is a scalar. Either you have a charge or you have no charge, and transport is driven by a potential gradient, and the logic is semiconductor-based transistors. You gain a lot if you switch from a particle-based transport, such as electrons, to waves. Because waves have an amplitude and a phase, so they have more parameters you can control, and the transport is simply given by wave propagation. And what you have in addition are, of course, all the interference phenomena which you might know. Waves can be anything. It can be, of course, photons, electromagnetic waves, a classic description, or it can be spin waves, the topic I'm going to talk about here. And of course, now what we have to address is simply just things like novel circuit design and realization of logic functionalities. We have done a lot of work in this field. I will show you a little bit later, but I would like to show you our most advanced thoughts about this, what could be done. So just very quickly, why spin waves? Why not photons? Why not plasmons? Or why not name it by yourself? Very simple. The wavelength goes down to the nanometer scale, frequencies up to several terahertz. That is very favorable, and this can be managed. Interference effects are very easily accessible, and information processing by interference, I think that is something I do not need to elucidate furthermore. Then, if you compare to optics, for instance, spin waves have the big advantage that the intrinsic nonlinear effects are very efficient. You know how difficult that is in optics. You always need to have a nonlinear medium, and the nonlinearity is usually rather small. We can realize macroscopic magnonic wave functions, Bose-Einstein condensates. I'm going to discuss that. We can operate at room temperature. With this, we are distinct from quantum computing, at least for the moment, where you need millikelvins. We can do it in insulators, so we are not moving charges and therefore no Julian heat. We can use concepts of wave-based computing. This all exists already in the literature. But you find, if you do a little bit of reading, that the footprint intrinsically can be made smaller. You can have all-wave logic. And what is also important in practice is that for magnonics, there are good converters to CMOS, so we can control via CMOS voltages or currents magnonic properties, and we can detect the magnons. And this leads actually to a field which some people simply call Magnon spintronics. So we have written a big review article which appeared in one of the Nature journals, which is titled Magnon spintronics. And what we have done in the past, and I'm not really going very much into the detail, is we have created logic gates. For instance, a majority gate, it has at the output or the majority of the logic values at the input. We have built a Magnon transistor. We have invested a lot into Magnon condensates. I will show you today the directional coupler. And if I say we, this means, of course, an entire team, but particularly it means Andrei Chumak, who studied this logic gates in my group before he became a full professor at the university at Vienna, where he now is working. So, if you think about Magnon computing, let's just put some very strategic conclusions here. Number one is, if you want to build a Magnon computer, it is certainly very favorable if you build on coherency. And coherency can be built in two ways. Namely, one, we work with coherently generated spin waves, so we need generic spin wave sources. Or we work with something which I would like to call intrinsic coherency, and these are Bose-Einstein condensates, where actually the coherency or the phase is the order parameter. So we work with nothing else than what you might know from other fields as macroscopic quantum states, which are well described by a macroscopic wave function. I cannot show you everything we have done, of course, in the given time. But so I picked two examples, two very different examples. The one is the interaction of coherent spin waves, and I will show you that an effect which you might not know, but which is well known in molecular physics, which is the STIRAP effect, that it can be used. And the topic here, excuse me, is macroscopic quantum analogies. And the other is, I was already indicating it, that we can use coherent macroscopic wave functions, such as from a Bose-Einstein condensate, to do some new type of computing. And I will share with you the first ideas we have to do some qubit computing. So something which is between quantum computing and classical computing, but in a very favorable way, I find. So, and of course, very important, maybe the most important view graph is the view graph of the people who do the work. You cannot do good science if you don't have good people. And the people who are in particularly important is Morteza Mohseni. He has done his PhD in my group, and he has done also computer simulation regarding Bose-Einstein condensates. He was the first in the world who could show that you can realize a Bose-Einstein condensate with the MuMax 3 code. Alexander Kreil is a PhD student, Halina is a PhD student, Philippe Perrault is a senior scientist in my group, who has supervised all kinds of work which was done in my group. Same for Vitaly Vasyushka, same for Alexander Saga. There is Dima Boschko, who started his PhD on the Bose-Einstein condensate, and he is now a professor at the University of Colorado. Shi Wang was a person who did all this directional couplers and the STIRAP experiment. He is now with Andrei Chumak, a postdoc in Vienna. And I would also like to mention the collaborators. This kind of work needs a lot of theoretical support. And I would like to name in particular Viktor Lvov and Anna Pomyalov from the Weizmann Institute, Gennady Melkov from Kiev, Andrei Slavin, Vasil Tibakevich from Oakland University, and more recently Arne Bratasch from the Norwegian University of Science and Technology. So let's get started. Also, first I will just discuss this STIRAP process, which you might not know. It has a big surprise with something which you might not be used from Magnonics as far as you have experienced it. We are talking about spin waves in waveguides. So we use waveguides for spin waves. Very, very similar, like you might know, fiber waveguides in optics. Also optical communication goes via optic waveguides. And the idea is very simple. We simply have a stripe of magnetic material. We always like to use yttrium iron garnet, YIG, because it has such a low damping. So it's a very good material for this purpose. And it is non-conducting, so we don't have ohmic losses. We apply a field, such as in this direction. We can apply it also in other directions. And we have a wire. And this wire can be connected to a microwave generator. So we have an input microwave signal. Then across the wire, we have the Ørsted fields. They oscillate with the frequency of the microwave generator. And these magnetic fields, they of course exert torques on the magnetic moments, which are here in the YIG waveguide. And in this way, a spin wave can be generated at the antenna and it can propagate. There has been a lot of work on this, and I will only show you one result we have done some time ago. Actually, this was in a nickel-iron waveguide. And what we can do, we can just calculate the dispersion for such a geometry. you might notice we have boundary conditions. For instance, the spin wave amplitude should be 0 here at the border of this waveguide. And then we can calculate the dispersion. And what we find is we get several lateral standing waves. For instance, one here, which is just only 1/2 wave. Then we have this red one with 1 node in the middle. We have this blue one with the 2 nodes. And then, of course, we can count the number of humps we have here. And therefore, we have the orders n equal 1, 2, and 3. If we calculate the dispersion, they are slightly different. You see this here. And now simply have an eye what happens if we now apply a microwave current, sinusoidal microwave current to the antenna. So let's say we do it with 7 gigahertz. Then we have 3 modes which propagate, first of all, with 3 different wave vectors. That is always frequency as a function of the wave vector. And you might also notice the slope here is slightly different between the 3 lines, and the slope is the group velocity. So these waves propagate with different group velocities. And then you can imagine that you get all kinds of interesting interference phenomena. For instance, what you see here in the background is a measured mode distribution, measured with time and space resolved Brillouin light scattering. And you see, for instance, a maximum here, but here you can even identify something like a hole in the distribution, and then the next maximum appears here. So all these phenomena, which you might know from a multi-mode waveguide, can be found here. So that is the introduction. And now let's do something more interesting. And that is, of course, coupled waveguides. And what you now see is computer simulations based on the MuMax 3 software. You see the reference here. And let's assume we have 2 waveguides, but we have now an excitation antenna only here where this little yellow stripe is. So no excitation in waveguide number 1, excitation only here in waveguide number 0. Here you find the parameters. And now what we can do, we can let the computer run, and what you find as a function of time are just patterns of spin waves. It's color-coded, so green means no amplitude, and red and blue means high amplitude. And you see something which you might identify from your background from optics, namely that a wave propagates here in waveguide number 2, away from the antenna, which is here, but it couples to the neighboring waveguide. And then after some time, it couples back into the first waveguide, and so on and so on. So you get an oscillatory behavior because of the coupling. The coupling here is simply via the dipolar fields, which are always associated with a spin wave. And what we can do is we can, first of all, just to remind you, we can compare that to a system you might be very well aware of, just a system of 2 coupled oscillators. You know very well, this is from Wikipedia, what happens in this case. The amplitude of the red pendulum is just reducing, and the energy is transferred to the green pendulum, and then after some time it just reverses, and it oscillates. The energy oscillates between the 2 pendula. And the same thing we have here in the waveguides. We can calculate it on a computer with real dampings, and you see if you move away, of course, the damping is always there. Damping simply means that spin wave energy is taken to the phonon system. You always have this effect, and this can, of course, be simulated. Just one parameter which is important is the coupling length, and that is just the distance between a maximum in one waveguide to the maximum in the other waveguide. So just this distance. Keep that in mind. That parameter will become important. And now you can play around with it. For instance, you can have 2 waveguides, very schematically shown, which you let interact only in this region, and here outside, the distance is too large for interaction. And then again, you can discuss what kind of modes do happen. And if you look into the dispersion, again, frequency as a function of the wave number, then we get 2 modes for the 2 waveguides, which are coupled here, and we can deconvolute these modes in symmetric excitations in the 2 waveguides, or in antisymmetric excitations in these 2 waveguides. And the coupling length, of course, is very important. These 2 modes have different dispersions because of the coupling. So here's the antisymmetric mode, the symmetric mode. And again, same game as we have done before. If you excite at a certain frequency, let's say here at 3 gigahertz, then of course, what happens is, oh, this is actually wrong. This should be moved up to here. So sorry for that. Then you see we have two different wave vectors. With, you can find the difference, and the slopes are slightly different. So the same phenomena like you have seen in the multi-mode waveguide before, but now in a two waveguide system. And now you can play around with it. For instance, you can change the frequency. You can create scenarios where for this given geometry, all the input power goes into the other branch, or the input power is split 50-50. Or the input power only goes into one branch. And the only parameter which we have changed between the three scenarios is only the frequency. So we get a frequency multiplexer, demultiplexer this way. Yeah? For instance, we can have two frequencies entering here. And if you put it right, the geometry, then you will only have the signal of frequency F1 here and the frequency F3, in this case here. So we get it really demultiplexed. So this works nice. One can do more. I have no time to go more into the detail. We can build interconnectors. We can build power dividers, multiplexer you have seen. So there is a large variety of applications one can do. But let me show you one application I find much more interesting. And that is just the stimulated Raman adiabatic passage. And what is the idea behind? Very simple. Let's take a detour to molecular physics or atom physics. And there, a very common problem is a three-level quantum system. So we have three quantum levels, 1, 2, and 3. And we would like to transfer population from 1 to 2. But that is not possible because in the given system, for instance, this transition is dipolar forbidden. And then you can think about lasers. You just take lasers with the right frequency so that you get here just transitions, the blue one and the red one. So you can transfer the population from 1 to a third level 3. You populate that one. And then with a second red laser, you transfer from 3 to 2. That sounds very straightforward. And so we pass actually via state number 3 and want to transfer the population. So what we do is, as a function of time, we first shine blue laser light into the system just to transfer from 1 to 3. And then we shine red laser light into the system, then we transfer from 3 to 2. It sounds very good. It is not very efficient. If the lifetime in this state is not good enough, very clear, or the standards considerations. But this is a very intuitive scheme, and therefore we simply call it intuitive scheme. Students have done it actually in Kaiserslautern in the group of my colleague Lars Bergman. This was 30 years ago, a time where I was not yet in Kaiserslautern, long time before. But what the students did is they made a mistake because they changed the order of these two laser pulses. So they did this experiment. First the red laser pulse, so from here to there, and then the blue laser pulse. And of course, it shouldn't work because the red laser pulse cannot transfer population because there is no population in 3. But surprise, surprise, it turned out that this counterintuitive scheme worked extremely well. And it can be very efficient even if the lifetime of the state number 3 is low. So, and that is called the STIRAP process, stimulated Raman adiabatic passage. In quantum mechanical language, what you do is you entangle these two states, and then, of course, you transfer population from state number 1 into these entangled states. And if everything is fine, all the population will finally end up in state number 2. So that is something we learned. And let's see what can be done. This can be described with a simple rate equations. I have no time to go through this. It can be realized in magnonics. And all we have to do is to replace the time coordinate now with a space coordinate. And the Rabi frequency, the frequency of the laser here in between, that we replace now by the coupling strengths. Now you notice why I put so much emphasis on the coupling strengths. So we replace the system with this kind of system. So we have 3 waveguides. Here is waveguide number 1. Here is waveguide number 2. And in the middle, we place now a waveguide number 3. So we want to go from 1 to 2 via an intermediate level or waveguide number 3. This idea is borrowed from optics, where it has been first realized by Stefano Longhi about 10 years ago. And again, if you look how this problem can be realized in some equations, you might notice the same symmetry in the equations. The Rabi frequency is now replaced by the coupling strength. Okay, So here is the experiment. That is our sample on the computer. And now what we can do, for instance, we can put a spin wave source here. Yeah, then the spin waves propagate here. They come close to the center waveguide, so the dipolar coupling sets in. All the population is transferred, and a little bit later, this population is transferred to the lower waveguide, and you see the majority of the population you find now as a strong signal in the lower waveguide. But notice that you also get the center waveguide here excited. You see quite some excitation here. And that is just the intuitive scheme. We first transfer from one to the intermediate and then to the third one. And now, big question, what happens if we realize the counterintuitive system? Here it is. Yeah, here is now same geometry, but the spin wave source is now placed on the lower waveguide. Otherwise, everything is the same. So we propagate. You see here, we transfer to the center waveguide at this position. But then obviously something happens, and from this position on, the population goes into the upper waveguide. And of course, you might consider it as if the wave would run backwards here in between, but I have to warn you that it's certainly not the right interpretation. What you now have to do is you simply have to switch your mind, and you have to consider this state here in this regime as one single coherent state, which you simply excite at one position and where you extract the population from another position. That is how you can understand it. The simulation here is just μmax 3, and μmax 3 is a classic code. So there is no quantum mechanics involved. Everything can be described by classical means. And what you have here, so this state here is actually named, is called a dark state. Dark state because the amplitude here in the center waveguide is very, very small here in this region and 0 outside. Now, if you have that, of course, we would like to ask, is it really true? And on the computer, we can do very nice experiments, which can be done in reality too, but which are a little bit harder to do. And that is we simply on the computer can increase the damping here of the center waveguides. And we make it here 50 times larger. Alpha is the damping parameters and in between. And if we now do the intuitive scheme, you see we have to really excite the center waveguide. The energy is taken out because of the damping, and very little goes to the other waveguides. So these are the three waveguides, the three colors, blue, red, and black for the three waveguides. But now, if we do the counterintuitive scheme, see what happens. All the population indeed goes to the other waveguide, and we only see the overall damping because of the finite coupling to the phononic system. We can do it as a function of damping. So Xi Wang has done here this calculation. And indeed, if we increase the damping in the intuitive scheme, everything is also damped very rapidly, but there is nearly no damping apart from the intrinsic damping now for the counterintuitive scheme. And that is simply the case because there is no excitation happening in the center waveguide, but we transfer across the center waveguide. So we transfer across dark states. So we now use states which are not populated for, if you like to use the word at this point already, for data processing. And this I find very, very exciting. So let me just summarize this part. So I showed you spin wave directional coupler, which can be important building blocks. And I showed you that this Magnonic STIRAP process can be realized. And it is the first demonstration, to my knowledge, of a device with coherently coupled building blocks and the formation of a magnonic dark state. So we calculate with states which are dark, which are not populated. But if the state wouldn't be there, of course, then we wouldn't have a transfer from the lower waveguide to the upper waveguide. And I think that has high potential for future magnonic device functionalities because it brings together quantum classical analogy phenomenon. That is another word for this kind of things with the control of the wave propagation. Of course, now you can use all kinds of means to control the center waveguide. You can add parametric pumping, or you can modify it with all different kinds of means. And this gives you, of course, good control, which you need for data processing using magnons. So you can do many things. You can test all different kinds of quantum mechanical phenomena. You can also go ahead and look into other atomic and molecular physics phenomena, which you can transfer here. Lots of these things have been done by Stefano Longhi And of course, we also have a small program just to continue this kind of work. But mostly we are interested in applying this. So let me show you the next big application. You might have realized from my talk how important coherent states are. And so we have to see what is possible. What is possible here, just let me see, I have to move here now a thing. I have a problem, I have a little problem. Okay, you can't see my screen anymore. I have a little problem, just a second, please. So now it's okay. Good. So now let's begin. I will show you that we can create magnonic macroscopic quantum phenomena in a very different way, and that we can operate with them. And this leads us to the field of quantum computing with magnons, with a small question mark behind, and this I will explain. So what I will discuss on a more general level is computing with macroscopic wave functions. So we need to have macroscopic wave functions, and the system choice is to use Magnon Bose-Einstein condensates. You might know from analogy how important macroscopic wave functions can be in other fields in physics. Think about superconductivity. Yeah, think about Josephson junctions. Yeah, there you have Cooper pairs. You look at their macroscopic wave functions. You let the wave functions interfere, and that is how you understand Josephson effects, for instance, the Josephson oscillations. We have to go to small feature sizes, that is very clear, but you all know if you have a system with small feature sizes, then you have induced quantization effects simply by the finite size of the objects. And today I would like to show you what this means for Magnon BECs. There are new ways how to create Magnon BEC, but I have not really time to go into this. That is rapid cooling. And then I will show you how we can use these BECs, these macroscopic wave functions, to create magnonic qubits and how to do calculus with these qubits. So main idea, find these wave functions. The analogy to superconductivity is I think very obvious. Also a lot of analogy to superfluidity. And just as a side remark is we can make the system dissipation free. This simply means that we can create Bose-Einstein condensates. I have to warn you, our condensates are always lossy because each magnon couples to the phonon system, but excitations on these condensates, they can be made free of dissipation. So what are we doing? Well, I have to provide some background, a Magnon spectrum for an in-plane magnetized film. So in such films, we get all kinds of magnons. What you see is a frequency as a function of the wave vector. And you see two characteristic geometries. One case is when the wave vector is parallel to the field. And the other geometry is when the wave vector is perpendicular to the field. Field means internal field or external field. Anisotropy is small, so the fields are parallel. Yeah. And then what you get for if the wave vector is perpendicular, so you get a mode, which is a surface mode, and you get all kinds of standing spin waves here on top. These are simply modes which travel forth and back between the front side and the back side of your film. We are discussing films here. And they are quantized because of the finite film thickness. If we have the geometry of parallel propagation, we get the backward volume mode. That is the name here of this mode. It first decreases and then it goes through a minimum and then increases again. So the physics of dipolar interaction tells us that the mode frequency should decrease, because in this way you avoid stray fields, dynamic stray fields, and they always cost energy. So with increasing wave vector, you reduce the stray field, mode frequency decreases, but then after a while the exchange interaction sets in, and these modes here are just driven by exchange energy. And you know, if you have pure exchange energy, the dependency of the frequency on the wave vector typically is quadratic, and you can already guess here some quadratic contribution here in the background. And what is remarkable, first of all, you see the slope here is negative. So the group velocity, which is a slope, is negative. So this mode runs backward in a sense, and therefore this mode is called the backward volume mode. And then most important for us today is there is a minimum frequency. And here are 2 points where the magnons have the minimum energy, the minimum frequency. And that is where we would expect Bose-Einstein condensation of the magnons. So now let me simply show you how we do it. We need to ask, we are doing thermodynamics, so we need to ask what is the population of these states. And the population is simply given by the Bose-Einstein distribution functions because magnons are bosons. So d as a function of omega is just the density of states, and rho as a function of omega is the density of occupied states. And the occupation is given by the Bose-factor with a characteristic -1 here. What you find here is a temperature, what you find here is a frequency, or h bar omega is the energy of the magnons, and mu is the chemical potential. If you have an open system like the atmosphere surrounding you, then the chemical potential is of course 0. But you see already the trick. The trick is simply make the chemical potential equal to the minimum frequency, to this frequency here, then this difference becomes 0. The exponential term becomes unity, and then in the denominator of this equation you have unity minus unity, which means infinite. So you have a divergence of the number of occupied states, and this divergence is just the fingerprint of a Bose-Einstein condensates. So we have to manipulate the chemical potential. That is a message now what we can get from this data. So how do we do it? Here you see again the population of this equation, just a quasi-particle density, that is a function rho as a function of omega. And here is omega, and this is plotted in a log-log fashion just to have a larger range which you can display. And if we plot this Einstein distribution function just with 0 chemical potential, we get this blue curve. Mind the minimum frequency here, you have seen before. And if we now make the chemical potential equal to h bar omega, then we see here's mu equal h bar omega, then we see the characteristic divergence as a fingerprint of a Bose-Einstein condensate. So how do we do it? There is a very convenient way how to do it, and that is simply just using microwave photons, just by connecting the system to a microwave generator. Each photon decays into 2 magnons with opposite wave vector, because a microwave photon on this scale has nearly vanishing wave vector, half the frequency for energy conservation. So we populate here these states, and then we have 4 magnons scattering. You can think of it like the scattering of gas molecules in the atmosphere surrounding you. So 2 incoming magnons scatter, and the 2 outgoing magnons are then the blue ones. And this happens under energy and momentum conservation. So basically we have an equilibration process here. And at the very end of this equilibration process, the magnons go here into the condensate if the conditions are right. So the key element is we can generate excess magnons via parametric pumping. They cannot relax within the system relaxation time. Therefore, the chemical potential becomes finite. And if the chemical potential matches the minimum frequency, Bose-Einstein condensation sets in. So this can be done in many different ways. One way is this is parametric pumping, but I would like to advertise we have done some other work. We call it timescale injection. That is simply we can just change the temperature of the system very, very rapidly, much faster than the relaxation time. And in this way, we disturb the system so hardly that again, this disturbance can be described by a chemical potential which equals the minimum frequency. So we wanted to understand these processes better. And therefore, I asked Morteza to simulate the process on a computer. So he has done everything on a computer using this MuMax3 code. So he has a film with all the magnetic moments. He has a wire where an Ørsted field is generated. Here you see the geometries a little bit. And then he can really simulate on his computer parametric excitation. So the excitation process. And what you see here is just the same you have seen before. What is changed is the film is made rather thin, only 85 nanometer thick, and therefore this is a fundamental backward volume mode, and this is the first and the second standing spin waves. The separation is simply larger because the film thickness is smaller. And again, you see the backward volume mode here, and it becomes exchange like here. You get the minimum here. And now he simulates parametric generation. So he excites magnons here with an excitation frequency of 4.2 gigahertz. So he generates pairs of magnons at half that frequency. So they are here. So let's see what happens. So after a while on the computer, he sees very nicely how all these states at this frequency are populated. Many here at small wave vectors, but you see also some population appearing here. Now, what he can do, he can wait a little bit. Then the 4 magnon scattering processes set in. So always pairs of magnons scatter into 2 other pairs. This can be pairs where one magnon is here, the other is there, or it can also be that one magnon is here and the other magnon is over there, always under energy and momentum conservation. And this leads to an equilibrium of the population in the states. We actually call the magnons here a magnon gas because the process of equilibration is so reminiscent of that what you know from the molecules in the atmosphere surrounding you. So we have that. So that is under pumping. And now what we can do, we can switch off the pumping. And then we see indeed in these computer simulations that condensates are formed. Here, all the population goes there at the minimum frequency. So we are very happy to have the condensate here. Actually, this result was disappointing for a couple of people. These are all the people who thought that Bose-Einstein condensation can only happen by pure quantum mechanical mechanisms. I showed you this was done using μmax3, and μmax3 is a classic code. It's Landau-Lifshitz. Yeah, so the proof here was made that Bose-Einstein condensation can be a purely classical process. We don't need quantum mechanics. Apart, of course, from the fact that the magnetism by itself is a quantum mechanical phenomenon. But once we have the magnons, the process of making a condensate out of it is a classical process. So many things can be done. We can measure the threshold properties for parametric generation, for magnon scattering, for the condensation. This we all have done, but I would like to skip that, but this you find in our publications. One simple experiment where we have generated a Bose-Einstein condensate using very rapid cooling. So we disturb the system now not by parametric pumping, but by cooling. And you see here the spot that is just again energy as a function of time. You see here how a Bose-Einstein condensate formed. From this experiment, we can actually derive the chemical potential. I only want to cut it short, but here is the experimental proof that indeed the chemical potential touches the minimum frequency here. So the condition what we had, that the chemical potential must equal the Magnon frequency in the condensate, we can even prove experimentally. So let's now go forward and let's use the last minutes just to show you that we can use it actually for something useful. And that is doing qubit calculus. You might remember what a qubit is. A qubit is simply a superposition of 2 states. Let's call them plus and minus state, with some amplitudes, complex amplitudes A and B. Yeah. So this superposition of these 2 states forms a qubit, and that can be used for qubit calculus. Okay, so how do we get these 2 states, plus and minus? Well, that is very straightforward. If you have listened carefully to what I was just discussing before, you might have noticed that the condensate always happens at 2 points, at a positive wave vector value and at the negative wave vector value. So I think it is straightforward to use the BEC plus macroscopic wave function as the plus wave function here, and the BEC minus wave function of the condensate here as the minus wave function there. If we do parametric pumping, we populate these 2 states, of course, equally. So one of our jobs will be how can we manipulate this? How can we, for instance, populate them differently? I should tell you how one very often represents this kind of qubit state, and that is by a point on the surface of the Bloch sphere. So the Bloch sphere is just a sphere with unit radius, The north pole is identical with the plus state. The south pole is identical with the minus state. So all other points here on the surface are just coherent superpositions of this north pole, and I'll call it the north pole and the south pole state. And we can describe it by two angles. One is a polar angle theta, which gives us a ratio of the amplitudes A and B. And the other is the angle phi, because A and B are complex amplitudes. So there's a relative phase between these two condensates. So phi is also very important. So we have two parameters describing it. That is just the polar angle theta and the azimuthal angle phi. At this point, the question usually comes up, is it quantum mechanics or what is it? It's classical, because I was already saying that the Bose-Einstein condensate is classical. So what can we do with it? Well, let's just do a comparison. In quantum mechanics, you have entanglement. There is no classical thing like entanglement, but it is not as worse as you might think. There is one phenomenon which is called non-separability. That simply means you can set up superpositions of wave functions, several superpositions of wave functions, and the joint wave function cannot be separated into these wave functions. So we can create what the experts know as Bell states, even with classical waves. The noise is different. We have quantum noise in quantum mechanics, and you have classical noise in real mechanics. Now, the very important part is a very fundamental algorithm is fast Fourier transformation. And of course, quantum mechanics is claimed to do this very, very efficient. There are algorithms around which do fast Fourier transform much faster than just Boolean logic, still not as fast as with quantum mechanics. And there are other algorithms, like for instance one for finding the secret n-bit string hidden in a black box, where you don't need this entanglement, or another key control distribution protocol. This goes very much now into the details. So that is all possible to realize with classical means. And also what is very, very important is the scaling behavior. One can show that using classical waves, we can escape from the exponential scaling behavior, which is very often claimed for classical systems. So we also have polynomial scaling. Okay, description is very often done via the Gross-Bitaevsky equation for the export. These types of equations, what enters is the dispersion coefficient, are interactions, which are the self-interaction between two magnons in a condensate, or the cross interactions between the two condensates, BEC plus and BEC minus. The external potential matters, also external forces onto the system might matter. And then we can do the simulations. And here is a simulation, Magnon density. If we pump the Magnon, we get a distribution over the entire spectrum. So we get the Magnon gas here. But if you let the system relax, it relaxes indeed into the BEC with this very, very sharp peak, which is just the correspondence of the divergence I was showing to you. And that is a really simulated picture of two condensates now in a very nice representation. Actually, these two condensates interfere. Here you get the interference patterns, and the most recent result we had is indeed that even vortices are formed. If you think about superconductivity as an analogous system, you know that vortices might form, and the same is the case here for our BEC macroscopic wave function. So the physics is very similar. So last minutes on cubic calculus. We have to do essentially two tasks. One is the initialization of a qubit, and second is to move a qubit state here along the surface of the Bloch sphere in order to have the calculus. We have lots of different mechanisms. One is wavevector-selective parametric pumping. The other is we can seed the Magnon BEC wave function with a predefined phase. I have no time to go into this, but I will show you the wavevector-selective parametric pumping, because this is a very nice thing. A very important tool here is a magnonic crystal. You might heard about a magnonic crystal. It's simply just a periodic disturbance of a parameter describing the magnetism in the X stripe. This can be, for instance, just an electric wire where you put a current through, so you have the Ørsted field around the wire. And then the external field is just periodically here manipulated. If you have that, then you have Bragg reflection, like you know from general physics, you have an incoming wave, and if an integer multiple of the wavelength of this wave matches twice the periodicity, so this distance a, then you get Bragg reflection, because there's a coherent superposition of all the reflections here from all these disturbances, and all the energy is done back. We have done this experiment many years ago. What happens if you have a Magnonic crystal, a gap is opening, and you know this from electronic band structure. You form also a gap for the electronic band structure just by the crystal periodicity. So in full analogy to that, we have the same here in our Magnonic system. And that simply means that if we put magnons here, they are scattered into the other gap forth and back. And indeed, we have done this experiment. So what Morteza has done, he has filled only one condensate. And then if he waits a little bit, again, frequency as a function of population as a function of the wave vector, if he waits a little bit, the population is transferred to the other BEC, and if he waits longer, it's transferred back. So you see very nicely how now the population oscillates between the two condensates. And that is very remarkable, because such oscillations, you know, from another field, from the field of molecular physics, atomic physics, these are the Rabi oscillations. In that case, the Rabi oscillations are between two energy levels. In our case, it's Rabi oscillations between two states which are separated by the wave vector. So the idea of the Rabi oscillations can be translated into the wave vector domain. And now, of course, we can use it to manipulate our qubit state, because we can transform population between the North Pole and the South Pole simply by applying an electric Magnonic crystal onto our sample for a given time. And we can, of course, select the time this way. There's even one more mechanism I would like to show finally, that in my view is a very neat trick to manipulate, also to manipulate the phase. And what we do here is again having our Magnonic crystal like you see here, and now we drive a microwave current through each of this wire. And the special condition is that the microwave current through the first and the second wire, they are separated in phase by pi/2. And the same between the second and the third, and the same between the third and the fourth, and so on. So here you see the phase differences. And if we do so, we create Ørsted fields which are now phase shifted. And I will show you what happens. What you see here is just a calculated Ørsted field in a very simple calculation. Here the white squares are just the wires which run into the film plane here in this case. And now we let microwave currents run through these wires perpendicular to the plane, which are shifted in phase, and see what happens. What you see is you get a pattern here of magnetic fields, of Ørsted fields, which seem to move from the right to the left side. So we have a moving induced magnetic field patterns. And that, of course, we can now use for our system. It corresponds that we shift the wave vector of our microwave photons by a wave vector provided by the Magnonic crystal. So here is now the wave vector of the pumping microwave photons. And now again we use parametric pumping, but now you see all the magnons which are generated by these photons at half the frequency. They are here in the green region, close to BEC plus and far away from BEC minus. So we populate only BEC plus. And if Morteza does this on his computer, indeed, he finds on the computer the population is here and not at BEC minus anymore. So this works very, very well. So we can create North Pole state. We can conversely create South Pole state. We can shift around. There are many ways how to shift now the intensity around and how to move along the block sphere. I have no time to go more into the details. What we have to manipulate is, of course, the position, the azimuthal, the polar position and the azimuthal position. And then we are able to realize a unitary operator such as the Hadamard gate. Here is just the Hadamard gate, which basically means that a North Pole state is translated into a state along the x-axis, and a South Pole state is transformed in a state along the minus x-axis here. This all can be realized Unfortunately, my time is over. I have to skip that. And finally, only outlook. Of course, a single qubit is not useful. We need to couple qubits in order to do real qubit calculus. The good thing is we can couple as many qubits as we want in our magnonic system. And the means we have for that is we can couple two BECs representing two qubits, qubit 1 and qubit t, via a gap. Then we have oscillations via dipolar coupling across the gap. We have done that to show the Magnonic-Josephson effect. We can separate two condensates. The condensate is always shown here in green by putting a control line with a DC current through it. So the Earth-state field of the DC current just creates here this gap in between. Or we can even realize something like flying qubits by having some wires. These wires have an induced signal and they can phase coherently transport the qubit information from the BEC between two BECs, BEC1 and BEC2. So that is all possible. So just to summarize, I hope I could show you that Magnon condensation behavior can be realized. We can realize a Magnon qubit this way, and we have already the initial recipes for the initialization of Magnon qubit states and for Magnon qubit protocols. So thank you very much for your attention.
Yeah, thank you very much for this exciting overview of this really nice physics, and we are really thrilled to see the Magnon Bose-Einstein condensation. So really great. So before we take the questions, I like to request Burkard to stop sharing, and I request all of you to switch on your camera. We will take a group photo now. So please turn on your camera. Oh, I see Wolfman here. Hello, Wolfman. Very nice to see you. Okay, great. Yeah, okay. So I take some screenshots. Please look at the camera. Cheers. Okay, I take one more. There are a lot of people today. Yes. Okay. Good. So just one more trial. Look at the camera. Say cheers.
Cheers.
Okay, cool. Thank you so much. So you can switch off your camera, and I request Burkard to again share the screen because there are a lot of questions I see, and now it's time to take some questions. So first question by Smriti Chawla. She is asking, are there simulations tried on OOMP also? Because you have shown the results mostly from UMax.
Yeah, we used, I mean, I'm not the expert in numerical simulations. That is more Tesa and Philippe Perrault as a supervisor, who are the real experts. They switched to MUMAX 3 because it was obviously more efficient to use or more versatile to use than just classical MUMAX.
Yeah, I mean, just to add,
I must say, I don't see any reason why it shouldn't work.
Yes, I think MUMax also uses the basic LLG equation, but only thing is it can take the graphic card, so the simulations are much faster than a regular OOMP.
Yeah, but this we do already because the computers we have, they have big graphics processors already. Yes. That is, I'm not the expert to comment on the technique how to do the simulation.
Yes, but I think it should be possible. Probably.
Yeah, it should be possible.
Okay, Saugata, you would like to ask, or should I read your question?
I can ask. Thank you for the talk. It was really exciting. So I wanted to know in the where you showed this counterintuitive scheme in the central waveguide. Actually, there is no spin wave when it is being transferred from the bottom waveguide to the top waveguide. Any specific reason behind this? Because in the other side, so can you please go one slide back?
This one?
Yes. So you see when it is coming from the intuitive scheme, actually the wave spin wave is coming from the top to the bottom And then we also see some waveguide like spin waves in the central waveguide.
Mm-hmm.
But that is not the case in the counterintuitive scheme. What is the reason behind this?
Yeah. Okay. Actually, if you look very, very carefully, you see in the interaction regime even some slight thing. It is all interference. I mean, you can call it interference. You can call it a coherent state. I think the best way to intellectually understand what is happening, just consider this here as one single state, yeah, which is of course distributed of the three waveguides, because everything is coherently coupled. Yeah. And then it's just a destructive interference in the center waveguide. Yeah. Of course, there are two amplitudes, one coupled from the bottom one to this one, and one coupled from here to there, but they interfere destructively, so that efficiently you don't see that. Yeah.
Okay.
You really have to think about one single object. If you like to stay in the particle picture, that a magnon jumps over to the central one and then jumps over to the top one, I think then you are lost. This doesn't
yes. Okay.
It is a destructive interference. Yeah. You can also think about it as a scenario that basically this is all designed in a way that if you have a wave here, it will couple to this one, but the more you move away, the longer becomes the coupling length. Yeah, so that at this point the coupling length becomes infinity, so that the wave which is here has no chance to couple back on the center waveguides. There are many different ways how to understand the system, just in a hand waving argument.
Okay. Thank you.
Okay, thanks, Agatha. There is another question by Akashdeep. He asked me to read it. When magnons can operate up to terahertz rates, then why does most of the examples shown here are only in gigahertz range?
Oh, very good. Very good question. Because there are several answers. Answer number one is we are still in the fundamental research domain. We want to discover these new effects, and then we pick a system where this is most easily possible. We have here the Bose-Einstein condensation. We need a minimum, and this minimum is essentially generated by a competition between dipolar interactions, low wave vectors, and exchange interactions, a larger wave vector regime, and it is just in a regime which we can easily access with our experiments. You can move it up to higher frequencies. You have to go to out-of-plane field geometries. We have done that, but this is of course much harder to investigate.
Okay, thank you.
There's no fundamental point. Of course, you can go to any higher modes. You can use, of course, antiferromagnets in principle. We haven't done it yet because this is still far in the future. But in principle, I don't see a barrier why you shouldn't be able to use just some high frequency states in the terahertz regime for the same kind of physics. And then, of course, everything will be much smaller, and which, of course, might also be of advantage. So that could work well.
Okay. The next question by STIRAP. Can you comment on relationship between parametric pumping intensity versus chemical potential?
I didn't fully understand the chemical potential and parametric pump. I think I understand the question. Yes, basically what you do, if you have an open system, like the gas atmosphere surrounding you, the chemical potential is zero. And the most easy way to manipulate the chemical potential is just generate an inequilibrium, simply by throwing, in our case, many more magnons into the system. And if you do it much faster, then the equilibration time of the system, yeah, then you describe that process by the chemical potential. You basically generate an inequilibrium, and the first order approximation to describe it is just working with a finite chemical potential. That's it. And parametric pumping is a very efficient mechanism to disturb the systems. That's all. Yeah. And again, I was very fast at this point because I had to save some time. But there are more means to do this, and one we also have investigated is just ultra-fast cooling, by cooling down the system much faster than the intrinsic relaxation time of the system. And this also works. And I'm very sure there are many other ways. I mean, one way we haven't tried is just using laser pulses from a femtosecond laser system. So you might come up with more ideas. Only the recipe is you have to disturb the system fast enough, and then you should see these kind of effects.
Okay, I think there are some questions people have raised hand. I have one question from intuition. If you go back kindly to the previous slide.
Here?
No, I think there was one slide where you change the frequency and then these modes are traveling in different channels.
Oh, this one, yes. Okay, yes. This one?
Yeah, this one. Actually, what is the reason behind this? The majority of the power goes in one or the other just by changing the frequency, because the dimension of both the channels are almost the same.
Yes. But it is. It was actually on the view graph before. It is simply that this coupling length is a function of frequency.
Okay.
That's all. You see directly if you look into the dispersion. Yeah, you see here just the two fundamental modes of the two waveguides. You see the first lateral standing spin wave. And actually this is wrong. So this should actually go here and there. Yeah. And then you see that the group velocities are slightly different. So the pattern change is a function of propagation, and also the coupling length changes. If you move the frequency up and down, I think then you can already infer that the distance here, this delta k varies, and therefore the coupling length will vary.
Okay.
I don't have a better view graph here, but I hope this is already convincing.
Yes. Thank you. Sobhan, please ask your question.
Yeah, that was a very nice talk, but I have a question regarding one of your last experiments where you showed this beautiful Magnon Rabi oscillations.
Yeah.
So in this kind of physics, you also see this collapse and revival of, if I directly correlate with the Rabi oscillations in atomic physics, you have this collapse and revival of the Rabi oscillations. So did you actually see such revival? I see the collapse. Did you actually see the revival of such Magnon oscillations?
Yeah. I hope we talk about the same thing. Let me just see. You mean, hey, where is it? I can't find my Rabi oscillations anymore. Oh, sorry, this was in the second part. Yeah, sorry.
Second part.
Yeah, sure. It was somewhere here. Very quickly, I'm there. It was just to show you the figure. So, this figure, you mean, yeah? Yeah, you see, I mean, we really, you see the population goes down, and then we have the revival here again, and goes down, and then it's back there.
No, I mean, the entire profile, this oscillations, this Rabi oscillations, this entire profile goes down. This is, yes. I would consider it to be the collapse of the Rabi oscillation. If I directly correlate.
Yeah, but you have to be a little bit careful, because this is a realistic calculation. Yeah, and realistic simply means we have taken into account the intrinsic damping of the magnons. Yeah, in this way, it's different. It's different from a molecular or atomic system where you usually take out the damping. Yeah, so this is not incoherence. That is simply intrinsic damping. You see, the time scale is a characteristic time scale what you always have for the damping. The damping usually gives you the order of one microsecond.
Okay. Yeah. Thank you.
Okay. Thank you, Sobhan. Are there questions by anybody else?
Yes, sir. I have one.
Braj, please go ahead.
I have one question. When you simulated the two waveguides, one you're saying they're a simulation, other you're saying they're theory. What is the difference between the two?
You see, I didn't fully understand.
You are simulating the two spin wave in the two waveguides. And
yes.
One graph you're showing through simulation, and other is through theory. What is the difference between the two? Theory and simulation.
The carrier and the carrier.
No, I think, Braj, your voice is not very clear, but I heard it. I can just tell his question. He's asking, in some cases, you are showing simulations and also showing some theory. So what is the difference?
Theory, yes, sorry.
And theory.
I beg your pardon. I didn't simply understand you well enough. Yes, this is all simulation. What you see here, the theory I showed is simply just a simple, very simple-minded. Where is it? Very simple-minded rate equations. What you see here, yeah, you find it in the textbooks. Yeah, that we simply take the population and takes the time derivative, and this is just giving here by this Hamiltonian And since the amplitude A is, of course, a 3-component vector according to the 3 populations what you have here. And if you have the same thing in our case now, then the time coordinate here is replaced by the propagation coordinate, which is the z coordinate, and then this just looks the same. That is basically all it is here. There's nothing. I wouldn't even call it theory. It's very simple-minded. Does this answer your question?
Yeah. Okay. Thank you.
Okay. Thank you, Braj. Is there any more question by anybody else? If not the case, then I request Burkard to please stop sharing your screen. I like to share my screen to present a small token of appreciation from our team. Okay, I hope you can see my screen.
Oh, very, very nice.
Yes, it would be very nice to welcome you in person in our institute in India. But for the time being, we like to present you a digital plaque. I will read it for you. A W2S seminar, webinar series on spintronics, Mysore, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Burkard Hillebrands from Technical University Kaiserslautern in Germany, in recognition and appreciation for being a very valuable speaker to give a lecture on advances in coherent magnonics. So thank you so much for your time. We all enjoyed. Today was a big hit. We have about 80 people joining the lecture. Thank you so much. And just an advertisement, next week we will have the lecture by Professor Vivek Amin from Indiana University in Purdue in US. But the time will be a little different. It will be 8 p.m. Indian time. That will be 4:30 p.m. CT. So see you next week. Please stay safe. And thank you so much again, Burkard, for your time and for this excellent talk. Thank you so much.
Thank you for listening.
Thank you. See you next week. Bye-bye.
Bye-bye.
See you. Bye.
See you. Bye, Wolfgang.